Welcome to the Explainer. Have you ever really stopped to think about how things hold together? I mean, from the steel in a massive skyscraper to the simple rubber in a tire, everything around us is locked in this incredibly complex dance of internal forces. Well, today we're diving into a really fascinating new framework that gives us a whole new language to describe that dance. It's built around something called the force tensor.
Okay, so here's our game plan. First, we're going to tackle why we'd even need a new way to talk about force. Then we'll get our hands dirty and break down the core pieces of this new framework. After that, we'll peek inside a material to see how it handles stress, see what happens right at the edge, and finally, and this is the exciting part, we'll see how this theory could actually jump from the blackboard into the real world.
All right, so first up, why a whole new language for forces? Well, the thing is, our current models are amazing, for sure, but they can start to struggle when you're dealing with materials that have really complex internal structures. And that brings us to a fundamental question. What if we had a more flexible, a more descriptive mathematical language? One that could capture not just the simple push and pull, the stretching and squashing, but also all the complex twisting and shearing forces that are so critical in so many modern materials. Well, that's exactly the question this new framework, called Postmodern Unified Theory, or UPT for short, is trying to answer. So, UPT is really a new way of thinking about all the forces buzzing around inside a material. And the absolute heart of it, the star of the show, is this powerful mathematical tool called the force tensor. It's what lets us describe what's happening inside with just incredible detail. So what in the world is this force tensor really? Let's jump into our next section and pop the hood to see how this one big idea is actually built from two simpler, more intuitive pieces. At its core, the idea here is actually pretty simple. It says that the total force inside a material, we'll just call it T, is really just made up of two different parts added together. You've got a bulk component, which handles all the simple uniform forces, and a dynamic or co-moving part that takes care of the more complex, twisty stuff. So let's start with T-bulk. This is the part of the force that we can all kind of get our heads around pretty easily. Imagine the deep ocean pressure squeezing a submarine from all sides at once. Or think about the nice, even pull you feel when you stretch a rubber band, right? Those are the kinds of simple, symmetrical forces that T-bulk is all about. Now, the second piece, TDC, this is where things get really, really interesting. This is the part that captures all the weird, lopsided, asymmetrical forces. Think about the twisting motion you use to wring out a wet towel, or the shearing force that grinds tectonic plates past each other in an earthquake. That's the kind of complex action that TDC is built to describe. So you can really see how these two components are a team. T-bulk handles the simple stuff, the stretch and squash, and its behavior is controlled by two functions. We'll call them A and B, which basically set the material's resistance. Meanwhile, TDC handles the complex twisting and shearing, and it's governed by a different function, H. If you can figure out these three functions, you can paint a complete picture of all the forces at play inside any material. Okay, so we've got the building blocks, the bulk, and the dynamic parts. Now let's look at the rules of the game inside the material. How do all these forces work together to keep something from just, falling apart? For any object that's just sitting still, there's a really basic but super important rule. All those internal forces have to be in perfect balance. Every push has a pull. Every twist has an equal and opposite counter-twist. In the language of this framework, they write this elegant little equation, div T equals 0. It just means everything's in equilibrium. But here's the kicker. Just saying forces have to balance isn't quite enough. Without one more rule, the math could actually describe some bizarre, physically impossible situations, like a block of steel suddenly deciding to turn into jello and collapse. So to stop that from happening, the theory needs a crucial stability rule. And that stability rule is, well, it's surprisingly simple. Remember that function B of I we mentioned, the one that describes the material's stiffness? For a material to be stable, the theory says that B of I must always be a positive number. It can't be 0, and it definitely can't be negative. So why is this so important? Well, you can think of a positive B as being the material's backbone. It's a guarantee that the material will always push back when you try to deform it. Without this rule, the math could describe a material with no backbone at all, one that would just crumble at the slightest touch. This simple little condition is what keeps the model grounded in the real, stable world we actually live in. So, we've set up the rules for what happens deep inside a material. But what about the outside? How does an object actually interact with everything around it? That's what we're going to dig into next. This framework doesn't just stop at the surface. It has a lot to say about what happens right there, at the boundary. It introduces concepts like surface energy, which is kind of like the energy cost of creating a new surface, and effective pressure, which is the pressure the material pushes back with. These two ideas are absolutely key to understanding how an object is sort of stitched into the world around it. So, what do you get when you add up all the internal forces pushing their way out and all the external forces pushing their way in? You get something the theory calls generalized traction. This is basically the total net force you'd feel if you could just touch one single point on the material's surface. And these boundary rules aren't just about forces. They're also about energy. They make sure that energy is conserved right at the surface, which prevents the material from just spontaneously creating or destroying energy out of nowhere. It's a critical check that makes sure the whole theory plays nice with the fundamental laws of physics. Okay, this is all incredibly cool in theory, but it brings up the million-dollar question. How could a scientist actually test this? How could they use it to describe a real material?
So how would you actually figure out what those mysterious functions A, B, and H are for our real material? Well, the source material actually lays out a really clever three-step plan. First, you'd apply a uniform pressure, like squeezing it from all sides, and that helps you find the A function. Next, you'd apply a directional force, like pulling on it from one side to zero in on the B function. And finally, you'd give it a twist to measure the H function. It's almost like a scientific detective story, where each step reveals another one of the material's secrets.
Now, to make it easier to compare different materials and different experiments, scientists can use a neat trick called dimensionless numbers. These are basically just clever ratios that tell you how important certain forces are compared to others. For example, one might tell you how important the material's stiffness is relative to its overall size. Using these lets everyone speak the same language, whether they're studying steel or rubber.
And here's the real takeaway. The moment you measure those key functions, A, B, and H, from an experiment, UPT completely transforms. It stops being this abstract idea on a piece of paper and becomes a powerful predictive engine that you can use for computer simulations and real-world material science.
And that leaves us with one last really exciting thought. By giving us this more powerful, more nuanced way to describe the forces inside materials, could a framework like this be the key to actually designing the materials of the future? Could it help us engineer things like self-healing airplane wings or ultra-lightweight body armor? The possibilities are just mind-boggling, and it all starts with just a new way of seeing the world.